Hello, my name is Anna Blood, and I participated in a 10-week research program supported by the National Science Foundation, researching multi-state organic fluorophores with Dr. Lei Zhu at Florida State University. The purpose of our research was to produce fluorophores that emit white light with potential to be used in electroluminescent-based lighting devices, providing energy-efficient lighting alternatives. And in order to produce white light, these compounds must be capable of multiple emissions across the visible spectrum at the three primary colors. Multiple emissions are capable by compounds such as hydroxyphenyl benzoxazole, or HBO, which undergo ground state and excited state proton transfers. In the excited state, the compounds undergo tautomerization to transform between the keto and the enol form of the compound. And in the in the ground state, the compounds can be deprotonated to the conjugate base form of the compound to produce anion emissions. So HBO is a compound that has been previously researched, and it's been found that the enol emission is around 370 nanometers, the keto emission is around 475 nanometers, and the anion emission is around 450 nanometers. And by adding a substituent to HBO, we are able to move these emissions to longer wavelengths of the spectrum in attempts to produce white light. Different R groups are used with different electron withdrawing and electron donating properties, and these different properties affect the acidity of the compound and therefore affect the compound's aptitude to transform between the keto, enol, and anion forms when dissolved in different solvents. And dissolving the compound in these different solvents results in the transformation between the three different forms. So in nonpolar solvents, the hydrogen on the hydroxyl group of the compound forms an intramolecular hydrogen bond to the benzoxazole portion of the compound, resulting in the keto emissions. And in hydrogen bond accepting solvents, the hydrogen forms a hydrogen bond, an intermolecular hydrogen bond with the solvent, resulting primarily in the enol emissions. And in hydrogen bond donating solvents, the hydrogen from the solvent in combination with the hydrogen from the hydroxyl group results in both keto and enol emissions. And in base, the compound is transformed to the conjugate base form by removing the hydrogen, resulting in anion emissions. So this is a photograph of one of the compounds in 7 different solvents, irradiated with a handheld UV lamp at 365 nanometers. And this is an emission spectrum of one of the compounds, and we can see that the enol emission is around 430 nanometers, the keto emission is around 550 nanometers, and the anion emission is around 530 nanometers. Compared to the HBO, the substituted HBO product, the emissions of the substituted product have moved to longer wavelengths, and we can also see that the anion has moved closer to the keto emission. And so by using different R groups, the anion has potential to move past the keto emission to even longer wavelengths of the spectrum in order to emit light at the 3 primary colors and produce white light. So to summarize, we're using organic synthesis to produce substituted HBO compounds, which are capable of multiple emissions, and we are modifying the substituent in order to move the emissions to longer wavelengths to produce white light. I'd like to thank my PI, Dr. Lei Zhu, as well as my graduate student mentor, Joe Hurley, for their guidance in this research, and I'd also like to thank the National Science Foundation for their support.